The fourth introductory problem set problem asks questions about if pressure remains constant. For example, pressure remains constant, velocity increases. What happens to y? Okay, so you basically have three variables here. You have pressure, you have velocity, and you have y, which is the altitude. So you have pressure, velocity, altitude within a continuous fluid. Now, this has to be developed slowly. You have to see a couple of examples, and we start with examples that just look at how Bernoulli's equation, which I'll talk about in a minute, allows you to relate the changes in two of the three quantities when one of them is constant. Two of the three quantities, P, V, and Y. Okay, well, let's go back a second now. Bernoulli's equation says that 1/2 rho V squared plus rho Gy plus P is constant. Now, 1/2 rho V squared is related to some of the things that we've done already, as is rho Gy and as is pressure. You put the ideas that we've looked at so far together and you get Bernoulli's equation. I'm not going to go through the details of deriving that, but Bernoulli's equation just basically is the conservation of energy. 1/2 rho V squared is very much like a kinetic energy term, except you have rho instead of mass. If you multiply by the volume of a fluid element, you get the mass of that fluid element. So I call this the kinetic energy term, or the kinetic energy related term. This would be potential energy if instead of rho you had mass. And if you divide or multiply pressure times volume, you actually get units of energy again. So without saying any more about it, this is basically like kinetic energy, potential energy, and other forms of energy. Okay, don't want to be too specific about that. Okay, within a continuous fluid, that means like you got water in a series of pipes, the water is continuous. You can get from one point to another, staying within the water. Many other situations that we'll see. Rho is the density of the fluid, and we're going to assume for now that rho is constant. That's pretty much the case when you're dealing with liquids. When you're dealing with gases, it's no longer so, and a gas is a fluid, so that Bernoulli's equation does apply to fluid, but it gets a lot more complicated because of the variability of the density of a gas. Okay, now, first question, if the pressure remains constant and velocity increases, what happens to y? Okay, so pressure remains constant, velocity increases. Well, if the pressure is constant, then since this plus this plus this is constant, and this is constant, that means that this plus this has to be constant. So if the pressure is constant, it follows from Bernoulli's basic equation that 1/2 rho V squared plus rho Gy is constant. If V increases then, if V increases, that means that 1/2 rho V squared increases. Now, if this increases, but this plus this remains constant, what can you say about this? Well, this plus this has to be the same no matter what happens to one or the other. So if this increases, in order to keep this sum constant, this part of it has to decrease. So we're going to say that 1/2 rho V squared increases. That implies that rho Gy decreases. Okay? Now, what if V, the velocity of the fluid, is constant, but y, the altitude of a point within the fluid, increases? Well, constant velocity means that what? It means that 1/2 rho V squared is constant, Well, okay, let's back up. Velocity constant means, again, certainly 1/2 rho v squared is constant. I was going to point back here, and that threw me for a minute. Okay, 1/2 rho v squared is constant. These three things add up to a constant value. If this doesn't change, then the sum of these two can't change, so that rho gy plus pressure is constant. Now, if y increases, that means that rho gy increases. And that implies that the pressure decreases. I'm choosing to put a couple of parentheses in here just to, the constant almost looks like it's a subscript on the P. Okay, again, this sum has to be constant, so if this part of the sum increases, this part has to decrease, the pressure has to decrease. Okay, looking at this purely formally, not talking about any specific instances at this point. Now, if y remains constant, what's that mean? That means that rho gy has to remain constant, so that this plus this, the 1/2 rho v squared plus p, has to remain constant. Then, if p increases, well, this part of this sum increases. The sum has to remain constant, so that this 1/2 rho v squared has to decrease. So that means that 1/2 rho v squared has to decrease. Now I'll observe also that if 1/2 rho v squared increases, rho gy decreases, and never mind that. Let's see. I guess I just wanted to talk about this. Okay. If 1/2 rho v squared decreases, that means that v has to decrease, because rho is a positive quantity. The only way 1/2 rho v squared then can decrease is if v squared decreases, and if v squared decreases, then v decreases. And up here, no, never mind. I keep thinking I see. Yeah, okay. Up here, if v increases here, that means that rho gy has to decrease, which means that y has to decrease. Now, if y decreases, that means you got to go lower. Okay, you're lower in the fluid. And again, we need to see how that works out in a number of specific circumstances. And we will do that a little bit later.